Okay, great. Let me start off by thanking the organizers for hosting such a wonderful workshop and for inviting me to talk. Right, so let me give a progress report on angle resolved transport in multilayer graphene. Right, the outline of the talk roughly this. I'll start to just briefly describe what angle resolved transport means, and as an introduction to this technique, right, let me tell you about how we can use this to identify rotational symmetry breaking, and also how this has been done in the past to identify potentially unconventional superconductivity. And then I'll move on to talk about something that's newer and maybe never done before, using angle resolved transport to identify directly probed time reversal symmetry breaking and also nonlinear Hall effect. Okay, so what is angle resolved transport measurement? I think angle resolved transport has been used a lot in strongly correlated systems where a spin nematic phase is a possible ground state, right? Because the nematic phase breaks rotational symmetry and you can use angle resolved transport to measure it. It has been done before in copper oxide thin film. This is the reference I reported here. They use a very unique sample geometry they call the sunbeam geometry. You take a very large film of single crystal and you pattern what this is. The center is just a single electrode and all these blue parts are the sample, right? So the sample consists of, I think, 36 Hall bar, right? Each one of these petals essentially is a Hall bar. With this kind of geometry, it allows you to flow current in different directions and measure longitudinal and transverse response as the current is flowing in different direction. Right, that angular dependence tells you something about the rotational symmetry of the system. And in order to do something like this, combined with our fabrication technique, right, this requires a sample that's roughly 3 by 3 millimeter. So if we want to use this to study van der Waals structure, either Moiré or a Moiré-less structure, it's essentially impossible. Right, so in order to do angle resolved transport in these materials that we're interested in, we fabricated a Pullman's version of a angle-dependent sample that consists of a disk with several leads. Right, this is a schematic of flowing current in one direction and measure longitudinal and transverse direction, transverse response associated with that current direction. And because the sample geometry respects rotational symmetry, you can flow current in different directions and do the same measurement, right? That gives you angle-dependent response. Okay, so with this geometry, let me tell you a little bit about what transport response is that tell you that rotational symmetry is broken, right? In copper oxide thin film, when you measure longitudinal and transverse resistance as a function of the angle of the current flow direction, you see that there is an angle-dependent oscillation in both longitudinal and transverse channels. And most importantly, when the longitudinal resistance is at maximum or minimum, right, transverse resistance had to be 0. And these define two characteristic directions. And because of this, these two channels are offset by about 45 degrees, right? This phase difference is quite important. I'll get to why in just a second, right? And in multilayer graphene samples, what I'm showing here is measured from twisted trilayer graphene near the magic angle at one specific density. Right, and I'm plotting longitudinal and transverse resistance as a function of angle as well. And these two red dashed lines mark the location, the angle of maximum and minimum value in longitudinal resistance. And as you can see, they match pretty well with the 0 transverse resistance. Right, and so this is the Cartesian plot of the angular dependence. On the right-hand side, I also plotted a polar plot just to save space. Right, because the transverse resistance goes positive and negative, so in the polar plot, they show up as this clover shape with red being positive and blue being negative, right? This is a very characteristic plot of showing this very characteristic angular dependence. So let me explain what this angular dependence means, right? These two lines mark the two characteristic direction. Along that direction, current flow does not induce a transverse resistance. Right? So using this angular dependence, we can fully extract what the conductivity matrix is right? If we use these two directions as x and y axis, then the conductivity matrix essentially looks like this. It has no off-diagonal turns. That's why the transverse resistance is 0, right? And the off-diagonal turn in this matrix happen to be hole resistivity, right? Or if you get the conductivity matrix out of it, what this means is that the Hall coefficient is 0. So even though in this angular dependence we get non-zero Hall resistance over many different angles, combining all the angular dependence together, we know that there's no Hall effect, and transversal symmetry must be preserved by the underlying electronic state, right? Okay, so once we have this technique has been used to probe potentially unconventional superconductivity in copper oxide, and this is also done by these two work before. And what they do is that they look at the angular dependence measured in the normal state, right? This measurement had to be confined in the normal state because you need finite resistance to do this measurement. And in the Cuprate superconductivity, they measure the angular dependence near the edge of the superconducting phase that's in the fluctuation regime where superconductivity has already onset, and compare that with the measurement, same measurement this is close to room temperature, right? And because of the nature of Cuprate, each one of these measurements is a different sample, right? So using many different samples, they can tune through the superconducting dome. And what their observation is this: in the normal state, close to room temperature, there is angular dependence, meaning that rotational symmetry is already broken at room temperature, so probably there's some kind of strain. But what their observation is, when superconductivity starts to onset, the principal axis, right, the characteristic axis that defines anisotropy, rotates sharply when superconductivity starts to onset. So what they're claiming is that the rotational symmetry breaking must be also intrinsic to the superconducting phase, and they're hinting at some kind of nodal superconducting order parameter, right? Okay, so as a proof of principle, we did the same measurement. What we did is in twisted trilayer graphene, we're parked at the optimal doping of the superconducting phase in magic angle twisted trilayer graphene, and we start to do angle-dependent measurement starting from normal state, and we cool down, right? And this arrow marks the onset of a fluctuation regime, right? Superconductivity starts to onset, that corresponds to this point. And as superconductivity starts to become stronger, the circle marks the angle of the principal axis. So as you can see, as superconductivity starts to onset, this anisotropy starts to rotate, which is very similar to what people reported in Cuprate material. In this system, we can directly probe superconductivity by doing IV measurement, right? So for example, these are two IV curves measured with current flowing in two orthogonal directions, and you can clearly see that the critical current vary by a lot, right? All of these are done at B equals 0, so there's no influence of B. And in fact, if I plot the color plot of all the IV curves putting together, extracting the critical current from the peak in the differential resistance clearly give you this cosine 2 theta dependence that defines the easy axis for the superconducting phase. And if you do this over the entire superconducting dome, right, the observation kind of is similar to, in the normal state here, it's 4 Kelvin. There's anisotropy in the normal state, but the anisotropy axis is density independent. And as you cool down near the superconducting phase in the fluctuation regime, you can see that this anisotropy axis, one anisotropy becomes stronger and the axis starts to rotate, right? And we can compare this to the critical current in the superconducting phase. The easy axis of the superconducting phase with the largest critical current align with the principal axis with the lowest resistance, right? So it all seems to make sense, and what this measurement is telling us, how much it's telling us up for debate, right? It's consistent with a nodal superconductor, but we cannot rule out the influence of a potential strain in the sample, right? That's always going to be a universal question. And if there's any suggestion as to how we can argue that way, that I'm open. I'd be happy to hear it. We can talk about that later. Right. Okay. So that's what people have done before, and we try to reproduce that. But angle resolved transport also tells us a lot of new things that hasn't been quite observed before. For example, time reversal symmetry breaking, right? Let me use banal bilayer graphene as example, right? Near the charge neutrality point of banal bilayer graphene, the band structure, the conduction and valence band touches at 4 point, right? This kind of geometry is ideal test bed for all kinds of different Coulomb-driven instabilities. And this has been explored very extensively in the past. A lot of the authors are actually sitting in the audience here, right? The idea of these really is that they use some kind of indirect transport indication to argue that at this point, either rotational symmetry or time reversal symmetry or both are broken, right? That's kind of what we can take in from the past. And once we have the probe of angle resolved transport measurement, it becomes a lot easier to kind of look at all of these all at the same time. So at this point, n equals 0, d equals 0, and also b equals 0, right? If you look at the angular dependence, it kind of look like this. There's something familiar, right? Both longitudinal and transverse channel have this angle-dependent oscillation that has a period of pi. But along this direction of principal axis, the black dashed line, the Rxy is not 0. Right? So using this angle-dependent measurement, you can extract the conductivity matrix. The diagonal terms determine shows these two terms are different. That shows that there is anisotropy, right? And the off-diagonal terms are also non-zero, shows that there is a Hall coefficient, right? So time reversal symmetry obviously is broken. So to test, right, you can use the Onsager's theorem for the linear transport. Because this is already along the principal axis, this matrix is anti-symmetric under transpose. That means that there must be a time reversal symmetry breaking term. To test this, what we did is that this is at b equals 0. We just ramped the magnetic field to negative 20 millitesla and ramp it back to b equals 0. And the same state, the angular dependence look like this, right? And now if you extract the conductivity matrix, the diagonal term is about the same. The off-diagonal term now flip sign, right? So this provides, what's remarkable here is that the longitudinal resistance is not infinite, right? It's essentially a metallic state. But now this has give us a method to identify potential orbital ferromagnetism, even though the longitudinal resistance is quite small, right? So with the metallic state now, we don't really have to rely on quantum oscillation. We can just directly look at the angle-dependent measurement to see if time reversal symmetry is broken. If that time reversal symmetry breaking connects to the orbital motion of electron, right? Okay, so we can look at this actually a little more carefully at the state at n equals 0, d equals 0. That shows large anisotropy and also a time reversal symmetry breaking term. If you tune away from n equals 0, d equals 0, very quickly, the anisotropy goes away, the oscillation in the longitudinal channel goes away, and also the offset in the Rxy channel also goes away, right? That suggests that rotational time reversal symmetry might be broken simultaneously, right? So what that means is that orthorhombic anisotropy, that's usually the culprit for anisotropy, does not account for rotational symmetry breaking, does not account for time reversal symmetry breaking. And the valley polarization, which is a very common order in multilayer graphene, it accounts for time reversal symmetry breaking, but it does not break rotational symmetry, right? So to break these two at the same time, you need something that kind of like momentum polarization. Although these two figures are highly exaggerated, you could have a momentum polarization that's more subtle than this and more physically realistic. Okay, so let me focus most of this talk on a different topic, nonlinear Hall effect, right? What I have shown so far are all in the linear regime, where the current is linearly dependent on the local electric field, right? And the prefactor essentially is this conductivity matrix, the 2x2 matrix, right? But in the physical system that we're interested in, there are lots of factors that could give rise to nonlinearity in the transport phenomenon, right? That will unlock the next term, the nonlinear term, where the current is quadratically dependent on local electric field, right? And when you have that, the prefactor now is, instead of 2x2 matrix, you have a tensor that's more complicated, that has 6 independent parameters. And so this presents both a challenge and an opportunity, right? The challenge is to understand what it means, and the opportunity is that there's now a new window for you to look into what the underlying electronic state potentially could be, right? And the most famous proposal in this nonlinear transport regime is the one that Liang Fu and Indy Saltman proposed back in 2015. They proposed that there is a quantum nonlinear Hall effect. Let me quickly explain what it means. It took me a really long time to figure that out. Okay, enough on that. But so the order parameter they propose looks something like this. The nonlinear current is quadratically dependent on the local electric field, right? But there are two things we should say about this order parameter. First, based on this, the quadratic or the nonlinear current is always perpendicular to local electric field, right? This is exactly comparable to the linear Hall effect, right? The current, it's non-dissipative. The current and the electric field are always perpendicular to each other. And secondly, this parameter has a vector D in it, which means that to have nonlinear Hall effect, you have to break rotational symmetry, right? This factor defines a preferred direction. So combining both of these together, it presents this is actually a very well-defined phenomenon that has a very strong condition, right? The nonlinear current had to be perpendicular to the electric field. Of course, Liang and Inti also proposed barrier curvature dipole as a possible mechanism, but I'll say more on that later. But the immediate challenge it presents is that how do we detect this, right? As experimentalists, we go to what we know first. To measure Hall effect, usually we flow current and we measure the electric field that's developed in the transverse direction, right? And if this electric field is in the second harmonic channel, then maybe that's nonlinear Hall effect. Like naively, that's kind of where we went. And indeed, there are lots of work that's done using exactly this method, right? Essentially, what they do is that they apply a current along the Hall bar and try to measure the transverse response and the longitudinal response, and in the second harmonic channel. And what they saw is that there is a non-zero transverse response and zero longitudinal response, and that kind of has been used as evidence for nonlinear Hall effect. But if you think about this a little more, something is a little off, right? The proposal is that the nonlinear component of the current had to be perpendicular to the current. And in this case, we just know that the linear current is along the horizontal direction. We have no idea where the nonlinear current is pointing, right? So to give you an example, a counterexample of why this doesn't work, if we were to calculate what the angular dependence for this conductivity tensor, sigma xxx, right? Nothing to do with Hall. This is purely in the xxx direction. If we were to calculate what the longitudinal response and transverse response is as a function of direction of current flow, right? This will be the expected response. And if you look more carefully, these red lines mark the direction where you have zero longitudinal response and very large transverse response in the second harmonic channel, right? So seeing this without the angular information, you really don't know what you're looking at. It could be sigma xxx, or it could be nonlinear Hall effect, right? So in order to say anything about what's happening in the nonlinear transport regime, we really have to do angle-dependent measurement. And more importantly, we need a lot of theoretical help to understand what the angle-dependent measurement means. So let me first tell you what our theorist collaborator told us, right? And that has proved to be critical to this a lot of work. So we come back to this ohmic law, right? The current has a linear turn and a quadratic turn, and this is a turn that we are interested in. To make it simpler, let's consider the linear conductivity matrix to be isotropic without any Hall, right? This is also solved for a general case, but this makes our discussion a little simpler. And our collaborator, the first thing they did is that they realized it's much easier to rewrite this. Instead of in Cartesian coordinate, they rewrite this in polar coordinate, right? And all of this then be broken down into three terms. So these are the linear part. Let's ignore them for the time being. If you look at the nonlinear term, there are these three parts. They're categorized by symmetry, right? If you look at the first part, the angular dependence look like this. It's threefold symmetric, right? If you look at the next two parts, the angular dependence are both one-fold symmetric, but they have kind of different chirality. What I mean is that if you look at the polar axis of the transverse term, they're rotated counterclockwise or clockwise compared to the longitudinal term, right? These two terms have different chirality. And this essentially gives us an angular basis for us to fit any nonlinear transport, right? Once you fit that, then essentially these parameters tell you what the nonlinear conductivity tensor is. We're trying to extract all of the tensor, right? And this is a little, if the physics is missing here, right, there's another way to look at this. If you notice, all of these parameters has one amplitude and one phase, right, in the imaginary plane. And so they can be rewritten as vectors. The first term can be represented as a vector. This vector can take any of these three directions, right? And the vector is essentially defined by this. And the next two terms can be defined as two vectors, b plus c and b minus c. This is where it gets really interesting. The b vector is purely dissipative, meaning that the transport response coming from the b vector, the local electric field is always parallel to the local nonlinear current, right? And the c vector is non-dissipative, meaning that the transport response coming from the c vector, the local electric field will be always perpendicular to the local nonlinear current. And this c vector is the nonlinear Hall effect, right? And this is the thing that a lot of people have been trying to identify, right? And also, the a vector has to be dissipative because a vector preserves rotational symmetry, so you cannot be nonlinear Hall. Right, that's pretty straightforward. And now we have these vectors. What we can do essentially is to take our transport response and fit it and then extract these vectors, and that defines what the nonlinear conductivity tensor is, right? So again, we use bilayer graphene as the test example, and we park ourselves somewhere in there that corresponds to the PIP2 phase, right, in the ND phase diagram. And if you look at the angular dependence of the longitudinal and transverse response, they kind of have this one-fold symmetric angular dependence, right? So rotational symmetry is clearly broken. And one thing I want to mention is that if you look at the points, we have roughly 16 points here, and we're trying to fit 6 independent parameters. You can argue maybe we're stretching it a little thin here. This is also another thing our theory collaborator realized, that you don't have to be confined to these two configurations, right? There's nothing special about longitudinal and parallel transverse in a disk sample. You can, in fact, take any leads as source, take any other leads as drain, and then measure a voltage difference across any two other leads. That will give you 830 points. I was extremely reluctant to do that because usually that's what's going to expose the downside of the sample. Right? But my students were brave enough to do all of that, and so I'm just showing a subset of the points. It's not practical to show all of them, but as you can see, even with some of the really weird configurations, right, the points fall right on the curve, and the curve is the fit using one single conductivity tensor, right? If you can fit all of the points with one single tensor, that means one, the fit is pretty good. We have a good handle on the tensor. Two, the sample must be very uniform, right? Yeah.
Yes, so I appreciate that. Since you had these various different vectors, can you explain how rich this tensor is? What is how many elements are there to the tensor?
2 elements. Each tensor has 2 parameters. Right.
So how many such curves are fit with one of the tensors?
So these are all fit with one tensor, and we can expand the points. Usually we take on the order of 100 to 200, somewhere between them, depending on how patient the students are. But once it gets to the 50, 60 points, I think the PIs are pretty happy. Right. So with the fit, right, we get a tensor, and now the interesting thing is what the tensor means. And so, right, here I'm just plotting the polar plot of parallel and transverse response, right, just taking two examples. And this breaks down into two components, A plus B. These are the dissipative ones, right? But based on the angular dependence, you can already see that A must be very small because this is the threefold symmetric term, right? And the C is the interesting thing. This is the non-dissipative component. This part must be purely nonlinear Hall, right? And and also give you a sense of the vector orientation. The B vector, the red one, is perpendicular to the C vector, right? Even though the C vector seems to be much shorter than the B vector, if you look at their Cartesian plots, the transverse response of the nonlinear Hall effect actually is comparable to the dissipative component, right? Another interesting thing is that if you look at the angular dependence of the nonlinear Hall parameter, there is actually a non-zero, small but non-zero longitudinal response. It is not true that nonlinear Hall has a vanishing longitudinal response. Okay, so this presents I think, a fairly definitive identification of the nonlinear Hall effect. And then the next question will be, what is the microscopic origin of this nonlinear Hall effect, right? So given the time constraint, instead of showing you all the data that we have, let me just walk you through our thought process. First, the nonlinear response is clearly anisotropic, right? So rotational symmetry is broken, which means that you cannot be skew scattering because this requires C3 being preserved. And also, the nonlinear response is actually enhanced with increase in D, which means that this cannot be quantum geometry because that will have an opposite effect, right? And the most importantly, inverting D does not induce a sign change in the nonlinear response. In fact, nonlinear response doesn't really care about inverting D, right? So that means it cannot be barrier curvature alone. In fact, we can show that even if barrier curvature dipole is there, it has to be a subleading term, right? So this kind of presents a conundrum, right? And then we're starting to look for answers to what could be the origin. One of the very interesting observation we have here is that if you measure nonlinear response and linear response at the same time, right, you can see the nonlinear response is clearly one-fold symmetric. It breaks rotational symmetry very strongly, whereas the linear response is almost isotropic, right? You can see a little bit anisotropic oscillation, but it's almost isotropic, right? So this is where our collaborator came in, and they actually showed a very elegant argument. What the argument is this. If you assume that there is an order parameter behind this response, and this order parameter delta break time reversal and rotational symmetry simultaneously, right? Following the Boltzmann calculation and using the Onsager theorem, they can show that linear anisotropy is a quadratic term, is second order in this order parameter, whereas the one-fold symmetric nonlinear term is linear first order in this order parameter, and three-fold symmetric term is third order in this order parameter, right? So following a fairly simple argument, this hierarchy is consistent with what we observe, right? What we observe is that there's a very weak linear anisotropy, very strong one-fold symmetric nonlinear term, right? And the conclusion really is that what it means is that whatever the order parameter is, it must break time reversal and rotational symmetry simultaneously, right? So the rest still is kind of an ongoing open question that we're trying to identify what is the order parameter that break rotational symmetry and time reversal at the same time. But we do know it's tied to the things that we're observing on a daily basis. For example, if you look at the ND phase diagram again, what I was just showing you is this point in the PIP2 phase. If you were to tune across this phase boundary from PIP2 to symmetry 4, right, this is the PIP2 and this is symmetry 4, the magnitude of the response decreased by quite a bit by increasing density. And most importantly, you can see a sign reversal, right? Almost every configuration reverse sign exactly. And so what that means is that both B and C vector rotate by roughly 180 degrees when you go from PIP2 to symmetry 4. And in fact, you can check this across the entire phase boundary at different d, that within the error of our identification, right, both B and C vector rotate, flip sign across this phase boundary. And across the phase boundary, what's changing is that the number of pockets is different, right? It goes from a half metal to something that's supposed to be everything's degenerate, but so the order parameter we're looking for likely is connected to this, although exactly how we're not sure at this point. I'm happy to talk more if you have ideas. Okay, so I think that's essentially all I want to talk about, but I do want to highlight the people who did the work, right? Experimental work is done by James and Aaron in my group. They're both senior students looking to graduate, so I'm kind of panicking as I speak. And a lot of the work, as you can see, has a very strong theory element in it. We've been staring at angular dependence for a long time without making much headways, and until Oscar and Dimitri stepped in and showed us how to do this angular fit to extract the nonlinear tensor, right? So I think most of the credit here goes to them. And yeah, and thank you for paying attention.
So first, really beautiful data and presentation as well, so congratulations. I was wondering about the superconductivity. Now, the basic assumption of all of this is that the conductivity is uniform in space, right? And when you're on this superconducting transition, this may be very not true.
Right.
Any thoughts about that? And a second sort of related thought was, for this nonlinear Hall effect, since you have this spherical basis, that's a natural thing, why not apply voltages that are in some sine wave going around the device and then measure currents? Is there a more direct way to only isolate the nonlinear part of the nonlinear Hall part of the response? Right.
Let me answer this question first. So the gold standard here is that if a sample is uniform, then it's very easy to fit angular dependence. Right, and vice versa. If the samples start to become really not uniform, then you won't be able to fit the angular dependence and extract a single conductivity tensor. There's actually one thing I didn't show that. Right, so at the beginning, the thing we start to do is that instead of just the longitudinal and transverse response, we do a very extensive measurement, like 50, 100 configuration. And if all of them can fit to the same conductivity matrix for linear or conductivity tensor for nonlinear, then we know that the sample is uniform. And that's kind of the criterion that we know even the superconductivity is onsetting, we can still do a pretty good angular fit. So it must be onsetting in a way that for the transport measurement it's uniform. Maybe microscopically has non-uniformity that's beyond our control. And I don't think I understand the second question.
You were showing something that there's a natural basis which is sort of spherically symmetric.
Yes.
And you do sort of 4 terminals, you apply voltage
yes.
and measure current somewhere. Why
right.
not apply voltage that goes around in a sine wave with different phases? So you have actually a voltage that has spherical symmetry. Good exercise.
Right. I see. Right. Yeah, I think the simple answer to that is we do the dumbest thing possible first. And then that sounds more intricate in terms of design, right? So maybe I'll talk to you after to figure out like what you can extract from that.
Okay,
yeah.
So it's amazing data that you showed. The one technical questions I have here is how do you know there is no trapped magnetic field here, any residual magnetic field that can break the time-reversal symmetry?
Right. Yeah, no, that's a great question. So the thing we do. I assume that you're referring to this measurement.
Yeah.
Right. So if you look at the Hall coefficient as a function of B, it's not linear. It has a very dramatic jump. Mm-hmm. And then if you sweep the magnetic field very slowly, there's a tiny loop. So this is actually great for the situation where the loop size itself is very small, right? And then if you extract the Hall coefficient, a regular metal will be linear with B, and something like this will have a very big step. And what we're looking at here is associated with that very big step that's slightly hysteretic.
So if you just convert that steps as if it is magnetic field, can you just estimate what is a residual magnetic field? If somehow your coil, coil is actually trapped some of the magnetic field there.
Right. Yeah. Oh, yeah. So it's on the order of 100 millitesla.
I see. So it's too large to explain.
Yeah.
Okay,
I think so. So we also have the same measurement for regular metal. It looks very linear.
Okay.
Yeah.
So for the conventional Hall configurations, all these papers with the nonlinear Hall effect, so I just want to clarify, are you saying you cannot conclude anything without doing this angular dependence regarding a nonlinear Hall?
Yes.
Yeah. You're saying yes, you cannot conclude anything.
Oh, yeah.
Okay, from just one doing the Hall measurement. Okay.
Yeah. The nature of a nonlinear tensor is that everything has their own angular dependence. And if you just look at one direction, there's no way that you can tell between these many different configurations of the tensor.
I see.
Dee, can you ask from there? Yeah.
So yeah, I have two questions. So the first, you mentioned that the order problem breaks time reversal and yeah. Should I? Is it on? Or?
Okay, I'm here.
All right. Okay. Okay. Thanks, Nia. So I have two questions. So the first one is you mentioned the order parameter breaks time reversal and inversion. But do you have a combined time reversal inversion? Like, do you see any linear Hall effect at all?
Yeah, I guess this is linear Hall effect. Or are you talking about the nonlinear Hall?
No, the linear Hall, because if you have time reversal and inversion, it would forbid the linear Hall effect.
Oh, yeah. I don't think I mentioned inversion. In this case.
Oh, rotation. Yeah.
Right.
Yeah.
Wait, you're saying if you break time reversal and rotation at the same time, then there shouldn't be a linear Hall?
Right. No. Sorry. If you have a combined time reversal and inversion, like TT symmetric, right? Yeah.
Right. Yeah. So if you only have value polarization but inversion is preserved, then there shouldn't be a linear Hall. But a lot of these, at least the second part of the measurement, there's always a large displacement field, so inversion should always be broken.
Okay. Yeah. So then my next question is rather a comment. I think if you break time reversal symmetry, then the like in terms of the expansion, in terms of the relaxation time, I think Liang's theory is specific for time reversal symmetric system.
Yes.
So he needs a tau in front of it.
Right.
But if you break time reversal, there's an intrinsic contribution that's entirely tau independent. So then depends on whether where your morbidity lies. So that term could overtake the tau dependent term.
Right. I think that's why I mentioned that even if barrier curvature dipoles, there is subleading. Yeah. For the nonlinear Hall effect that we observe, I believe that barrier curvature alone is not the answer.
Yeah, thanks.
Thanks, Leo. I have two quick questions. The first one, for the linear stuff, it seems that you had, when in your angle dependence, you had more data points than your number of leads. Can you comment on that? And then the second one is for the nonlinear stuff. Can you comment on the side jump mechanism? Side jump mechanism, if that applies for the nonlinear Hall?
What's side jump mechanism?
Okay, never mind. Yeah.
Skew scattering?
So you ruled out skewed scattering,
right.
And you ruled out the intrinsic barrier curvature dipole, but there's also side jump.
Yeah. Right. So great question on the first one, and I was hoping not being called on that. In this configuration, right, where we source current between two leads that are 180 apart, there's only 8 points. But in this measurement, what I did is that I combined this configuration, use source string, and measure between these two. In the data that I didn't show, right, these are two configurations. We fit them independently. And if you use a single conductivity matrix and you fit them, you realize they are off by about 10%. So the 10% difference, if I plot them together and fit a single line, it's almost hard to tell, right? So I cheated, and you call me, and yeah. But in the full formula, in this more extensive measurement, right, there's no cheating, right? We're fitting everything based on their geometry. And in the nonlinear measurement, I'm only showing you each configuration. There's no cheating there. Yeah. Maybe let's talk afterwards. I don't know that mechanism. Maybe I know that by a different name.
I have a question about the last part with bilayer graphene. So going along with the interpretation of the this coming from an order parameter which breaks time reversal symmetry, did you try to train this with an out-of-plane magnetic field or a strong in-plane magnetic field even to see if it has any response?
Right. So yeah, I guess that assumes. Here's the thing. That assumes there's a magnetic order that you can train, and there's hysteresis in there, right? But if you look at the linear response, if there is a Hall coefficient, it's very small. So I think this is what's remarkable of nonlinear response. It's a subleading term to the linear matrix. If there is a order parameter that breaks time reversal symmetry, it must be a very small one that we cannot detect clearly with the Hall resistance, right? So, and regarding the training, magnetic field training of this, it's kind of an ongoing process. There could be time reversal symmetry breaking that doesn't couple to magnetic field, and yeah.
Yeah, but like I'm thinking, in terms of the small pocket polarization, that might couple to an in-plane magnetic field.
I
so
see.
that's something that
I see. Right, you're talking about momentum polarization.
Yeah, momentum polarization.
Yeah, but so if linear response look like this and nonlinear response look like that, that means it cannot be a full pocket polarization. It has to be a more subtle configuration, right? But you know that's I wouldn't say we can rule that out, but that's something that we're working on right now.
I have a question about the experiment. So how easy it is to fabricate a sample that can have such homogeneity? Do you have any experimental way to improve that?
Right, so there's a reason that I'm showing most of the measurement on banal bilayer, right? So the homogeneity is fairly low. Yeah. So far, all the banal bilayer that we looked at, 4 or 5 different devices, they essentially all have the same response. For graphene Moiré, twisted trilayer, twisted bilayer, the success rate is lower. Yeah.
I see, like how low it is?
I think out of maybe 10 samples, 3 or 4 shows very uniform response.
I see, thank you.
Yeah.
Any last question?
Hey, Leo.
It's about 2 micron in diameter of the disk. And we intentionally make it very small to minimize inhomogeneity.
Yeah, I have one quick one. So you have 6 free parameters in your nonlinear tensor. And if you study temperature dependence of some of the coefficients, can you infer, like, when does the order parameter breaking, symmetry breaking sets in, for example, in a PIP2 phase?
Right, yeah. So most of these nonlinear response, it onsets below 5 Kelvin. But we haven't done a full analysis to extract the temperature dependence of each parameter. That's something that we should do.
Okay. Yeah. And that could potentially rule out strain effects, do you think?
For the nonlinear response, strain cannot be the dominant. Strain alone doesn't give you nonlinear response. You need something else.
Okay.
Yeah.
Thank you.
All right. Thank you so much, Leo.
Thank you.